we introduce Explainable XR, an end-to-end framework that can capture, analyze, and visualize multimodal behaviors of users in XR environments. Imagine you're developing an XR application, and there's a way to easily analyze what the users of the app talked about and interacted most with. By understanding the users, the application can further tailor to the needs of the users. This would greatly contribute to the community of extended reality, visualization, and ATI. The interactions in XR are different from traditional computing. The users in XR don't simply click buttons. They interact physically with objects through gaze, gestures, voice, and movements. We need a framework that not only tracks the button clicks, but also captures the multimodal interactions. Also, it must interpret the user's behavioral pattern in a more insightful way. Existing works have addressed the similar requirements and challenges. For example, Argus captures users' interactions and provides an analytical tool for visually debugging machine learning models in augmented reality. Plume proposes an end-to-end framework to record, replay, and analyze user experiences in XR. It offers both in-situ and ex-situ retrospective visual analysis of the users, as well as recording physiological and spatiotemporal data. Lastly, Relift provides a visual analytics tool for user studies conducted in mixed reality. It gives the researchers the ability to review the user session, measure performance, and load the environmental context of the scene. The three works contribute significantly to the analytics of users and successfully collect multimodal user data streams. However, they were limited in providing a generic purpose framework that can be used for a spectrum of XR environments. Also, they have difficulty in capturing the cross-reality and collaborative scenarios where two or more users are present. To fill those deficiencies, we introduced Explainable XR. Explainable XR was designed to easily record the multimodal properties of user data streams across virtuality and multi-user scenarios. Then, we process them as well as visualizing them on our dashboard. To capture user interaction data consistently across all virtuality, as well as for single and multi-user applications, there must be a well-structured data format that can describe every user action. So we focus on the user's interaction patterns of XR. We find that the user information of XR is always triggered by the user's actions. Let's see one example to understand what that means. A maintenance personnel entered the basement with an AR head-mounted display to see the AR inspection note from last week. We can see that the entrance action here triggered the loading of the data in the AR system. The C action, the movement of the camera or the gaze, triggered the rendering of the data to the user's head-mounted display visor. And lastly, the memo was instantiated with the situation action of the user. Learning from this, we design a user action-oriented structure called the User Action Descriptor, or in short, the UAD. The UAD format always starts from a user's action. The rest of the information revolve around this action. We follow the Kipling method, or 5W1H method. We also store the contextual interaction data, such as the referent the users interacted with, the historical actions, and the scene captures. Using our UAD format, we can now capture the user's information regardless of virtuality or single and multi-user scenarios. Also, because we bind all user data to an action-oriented hierarchical format, this helps us transfer the data to the LLM for an AI-guided analytics. Now, the UAD format is intuitive and easy to use, but in case the users find it difficult to use, we also designed a GUI Unity plugin. You list the user's actions you wish to capture, and our plugin auto-generates a boilerplate Unity C# code, which minimizes your effort on understanding our UAD format. Or of course, you could manually define a log in your code. You include this script in your XR application, and it will store the data on device at the end of the session. Once the data is captured, we process and visualize the user data onto our analytics dashboard. Our dashboard consists of 5 main viewers that visualizes the data derived from the UAD format. The spatial viewer shows the spatial patterns of one or more users in various XR scenes. The temporal viewer visualizes the user's events in historical order. The data viewer and plot viewer show the unprocessed data streams as well as statistical visualization. Furthermore, we provide a set of LLM-generated insights through the Insight Viewer. This facilitates the analysts for more effective data exploration. Explainable XR can capture a series of multimodal data streams from one or more users across XR environments. This means the dashboard can easily become overloaded with information. To mitigate the information overload, we provide LLM-generated insights that is tailored to the needs of the analysts. The analysts can optionally provide a prompt that specifies their topic of interest, and we provide a pointer to the data you might find interesting. We tested our framework on 5 different applications across VR, AR, and MR applications. We also proved the versatility of our framework by testing our framework on Apple Vision Pro, Meta Quest Pro, and iPads. Our user studies show that Explainable XR is an easy-to-use framework that effectively visualizes the summary of user information. Also, it shows that it does well on providing situational context behind every action and pattern. Then, the users also found our LLM-generated insights helpful. In our technical evaluation, it showed that our framework is able to maintain real-time performance. For more detailed information of our framework, please refer to our paper. Thank you.